Chapter 8, Exercise Set B. This exercise set is rather peculiar in that you have to use two or more different methods for the same problem. Here is the context part of problem 1, this one. This part is exactly the same as that of problem 2. What's the difference? Problem 2 uses 2.1 through 2.5 as a guidance to the problem, and problem 1 you have to use 1.1 through 1.5 as the step-by-step process. In short, you are doing the same problem in two different methods. After that, we are going to go over Appendix 1, which is still different method, the same problem here, and Appendix 2, given time, still different method with the same problem. About problems 3 and 4, they are identical too, but I'm going to leave these two problems to students. We'll just do problem 1 and 2 and Appendix 1 and 2. Okay, let's begin. Problem 1. Do you drink the recommended amount of water each day? Most Americans don't. Americans drink 4.6 8-ounce servings of water each day, which corresponds to 36.8 ounces. A sample of 42 education professionals was randomly selected and the water consumption for a 24-hour period was monitored. The mean amount consumption was 39.3 ounces. Assuming the amount of water consumed daily by adults is normally distributed and the standard deviation is 11.2 ounces, is there sufficient evidence to show that education professionals consume, on average, more water daily than the national average? Use alpha value as 0.05, and as you can see, this came from our textbook, letter by letter. As a matter of fact, I just put this part in, otherwise exactly the same. And our textbook actually gave us the source where this one came from. Okay, let's begin. 1.1, explain why the normal distribution, also called the z-distribution, is appropriate. Number 1 is partly a theory and partly a hint. Even if you cannot answer 1.1, you can use z-table and z-curve, this one in particular, to answer the other parts. But let's talk about the theory. Now, why can we use the z-distribution or the normal approximation? There were two cases when we could use normal approximation, roughly speaking. Large sample size or known population standard deviation. Which is it? Sample size of 42 is not going to be the first, it's going to be the latter. Population standard deviation is known. 11.2 corresponds to population standard deviation, not sample standard deviation. Why? 11.2 did not come in the same sentence as 42 education professionals. If it came here, then it would be sample standard deviation. But it came with this part, assuming the amount of water consumed daily by adults is normally distributed and blah, blah, blah. And this one is not about education professionals, just American adults. So this corresponds to population. So it's sigma, not s. This is the short version of the answer, and that's going to be sufficient for full credit in 1011 math course. But if you're going to go a little deeper, well, here it is. There are two situations that normal approximation applies, and here's the first. The inference is about the mean. Is that right? Yes, we are talking about the mean amount. On average, yes, mean. So this one checks. Number 2, it's about simple random sample. Yes, random is selected, so we are guaranteed with doing the same thing over and over again independently. Independent and identically distributed. Okay, finally, large sample size. Uh-oh, there's a problem. We have only 42. That's way too small for central limit theorem. So the first criterion doesn't work. Let's go to the second criterion here. About the mean, yes, we saw that. And then the population is believed to be normally distributed. Is it? Yes, we have this assumption here. Okay, that one checks. And finally, we have population standard deviation. Okay, so second criterion applies. This is a bit better answer. But of course, in 1000 level, I will accept this short answer as full credit. Next, let's set up hypotheses. Null hypothesis. What does that look like? We typically use Greek letter mu for population mean, and that's approximately equal to a certain number. I don't know that number, so let's tentatively name it as mu0. Now, what is this mu0 here? What's a candidate for this one? Look at the problem, read through the problem, and then how many onses are there. Actually, this one was given as a hint. The original problem in our textbook didn't have this 36.8. It simply says 4.6, 8 ons serving. From that, you had to deduce it was 36.8. This problem this insertion made this problem a little bit easier because you have a candidate here right away without thinking. And there's another candidate, 39.3, and one more, 11.2. I don't think there is anybody who's going to be confused with this one. This is clearly the sample size. That's not it. So we have 3 onses here, 16.8 ons, and then 39.3 ons and 11.2 ons. Which is right? Well, which is wrong? This says standard deviation, so that's clearly out. We are down to 2. A little bit trickier. The answer is 36.8, not the other one. Why? This came from the sample. This is called a null hypothesis. And what does the dictionary meaning of null say? Null is associated to nothing. So you have to do nothing. But in order to get 39.3, you have to do something. You have to take the sample and do some work. This is not null. Null hypothesis cannot come from sample. It just came from the problem out of nowhere, even if you did nothing except for just reading the problem. This is null. So 36.8 is the null hypothesis, the null value. And alternative hypothesis, okay, it's got to be the other one, right? $39.3. Is that right? This is null, so by default, this is going to be the alternative. Wrong. This is not the way hypotheses are set up. These two numbers must always be the same. Once the null value 36.8 is selected, that should come down to alternative as well. Now the difference takes place right here. Mu is not about the same as 36.8. It's going to be either significantly bigger or significantly less or meaningfully different. Which one is it here in this case? Read the problem. It says more water daily. Do you see that? So it corresponds to more, meaningfully bigger, significantly bigger. As a matter of fact, just different case, the third case is rather rare, and probably I will not write that kind of problem in a 1000 level course. I may, or I just end up copying from textbook and then it may slip into the exam problem or quiz problem or anywhere, so I do not make promise, but still I don't think just different. The third case is the representative of hypothesis testing. Most of the time it's one way or the other, significantly bigger or significantly smaller. The reason is because we already have the sample mean, and that's bigger than 36.8. So just being different, it doesn't make much sense. If you didn't know the sample mean already, okay, in that case, you don't have any guess one way or the other, so you may set up your hypothesis like that. But if you have X bar value given here, then it's going to be either bigger or less, and certainly 39.3 is bigger than 36.8. Anyway, this is the answer key here. There are two indicators. One, more important of the two, the problem explicitly says more water. Number two, 39.3 X bar value is bigger than 36.8. Okay, we have hypotheses set up, so let's go ahead with a picture. Here's a normal picture, and how do you draw the normal picture? Here is the step-by-step process. Outline, center, end, and then finally shade. Here we go. Outline, you draw the normal picture, going up and down like this, unimodal, symmetric, and so on. And what's the center? Null. Null is always the center, 36.8. Now, and that's where we have some difference between one method and the other method. This method is about critical value, so critical value goes right here at the end. And that represents a threshold between the null region and alternative region, which are represented in blue shading and red shading respectively here. What do you mean by null? Well, close enough to the null value 36.8, and alternative too far away so we can ignore null. And if you have this critical value, X value, then you can compare that with observed mean of 39.3. If 39.3 falls into the blue region, as I'm pointing my mouse right now, then null wins. The blue represents null. Now what if 39.3 falls to the red region? Then alternative wins. Red region corresponds to the alternative. So it's easy to distinguish one and the other. Close enough to the null or too far away from the null. Depending upon the distance, you get either null hypothesis or alternative hypothesis. Now that threshold is the critical value. Now how do you find out its critical value? Exactly the same way you did for confidence bounds. Do you remember doing this? Z equals to end minus center over standard error. And in this case, end is this X value, center is 36.8, and standard error, what is standard error in this case? In general, it should be standard deviation, sigma, over square root of n. The sample size is n. So in this case, this is 11.2, and this is 42. And this quantity should be equal to the z-score associated to this picture, 95%, 5%. So what z-score corresponds to 95% to the left-hand side? Let's go over to the z-table. It's in the second page. 95% right here. 1.64, 1.65, somewhere in the middle, because this is kind of push. So let's estimate it as 1.645, and let's solve this equation with respect to x, then we're through. Let's actually go do that. Here we go. I'm copying and pasting the same picture we saw before. And this is the equation we discussed. How do we solve it for x? Flip the denominator to the other side, and then flip the center to the other side, and we have this kind of computation. Run your calculator, you get something like this, 39.64 something. So this threshold, critical value, is 39.6 something. Now, it's easy where 39.3 falls. It's a little bit smaller than 39.6. It falls right over here in the blue region. So which one wins? Null or alternative? Here is the conclusion. The null hypothesis wins. This is a question you have to ask. Too close to null or too far from null? Close enough to the null. Too close to null, so you cannot reject null. You have to accept null hypothesis. Null hypothesis wins, alternative hypothesis loses. There are many different ways to say that, but probably the most formal way to say it is kind of like this. Fail to reject the null hypothesis. There is not enough evidence to overturn the null hypothesis. Okay, there can be many other ways to say. This is just two of the formal ways. Well, this is math class, and I'm far more interested in the mathematics behind it. So if you use a little bit more informal term like we select null hypothesis, or even null hypothesis wins, H0 wins, I'll accept any of those with full credit. Be careful. Maybe not all instructors would. Some instructors may prefer a little bit more formal languages. Well, in that case, you simply have to follow that. In my class, I'm far more interested in mathematics, the theory behind it. So conclusion part is not that much of a problem. And as a matter of fact, I was a little bit premature in killing all these windows. Let's go back to this picture. Here's a theory behind it. Well, you draw normal picture and null goes to the center. You're looking for the critical value, the end. So how do you find out the end? The way you found out confidence bounds. Exactly the same way we used to do before. Once the confidence bound, or it's not confidence bound, excuse me, once the critical value is found, you can compare that with observed mean. An observed mean can go either blue region or red region. So H0 may win or HA may win. In this particular case, H0 ended up with the winning hypothesis.